Welcome to the series of lectures regarding power system modeling in ETAP. In this series, we will be covering system modeling, that is power system modeling in ETAP. And in the second part, we will be looking at load flow analysis in ETAP. The third portion will be comprising of short circuit analysis, balanced and unbalanced faults in ETAP. And the final part will be the protection system settings, and to be specific, the settings of overcurrent and differential relays, how we can achieve them in ETAP. Coming towards what the introduction of what is a power system. So this is a basic layout of what elements a power system comprises of. We have the generation, which generates electricity at some intermediate voltage, and then with the help of step-up transformers, we convert the voltage into extra high tension, that is EHT. Like in this particular example, we have two generators. The first one is generating electricity at 11 kilovolts, and the second one, which is a swing generator. We will be talking about this swing mode later in this video. The second generator is generating electricity at 13 kilovolts. Then with the help of step-up transformers, we are stepping up this electricity into to 132 kilovolts. And then we have a double circuit transmission line comprising of 100 kilometer length. And then we have a power transmission that is again stepping down this 132 kV voltage into 11 kV. And then we have the distribution feeders. We have considered the lump load here. To be specific, these are not lump loads. This is shown in figure C. As you can see here, this is the portion. Like we have 11 kV feeders originating, and then we have either overhead line or distribution cables. And then we have the distribution transformers, which convert 11 kV voltage into household use voltage, that is 440 volts or 0.44 kV, and then we have the 0.44 kilovolt loads. But we have considered this whole portion as lumped loads in our single line diagram. So we have the generation, step up transmission using transmission lines, overhead transmission lines. Then we have the power transformer. This is basically a place where a grid is situated. And then we have the distribution lines, which we have considered as lumped loads. Now let's move on towards ETAP. We will be using version 12.6 for our videos. Let's go on to create a new project and name it as test project. So this is the editor mode, and from here you can find the list of all the elements that you want from your SLD. These are the analysis tab in ETAP. Moving on towards the SLD, this is the system that we will be modeling on ETAP. First, it has two generators of 11 kV and 13 kV voltage rating. So let's select synchronous generators. Let's drag and drop these, and since we will be plotting the SLD in horizontal mode, so it will be better to have it rotated. Like we go on to rotate, and it's rotate and 90 degrees, rotate 180 degrees. So we can just copy and paste this generator. And name it as generator 2, or we can simply name it as G2 also. G2, and this will be G1, right? Next we have to select the HT circuit breaker. Again we need to rotate it. We can just copy and paste this circuit breaker. The next element in the SLD is a transformer. Then we have a transmission line, and then we have a power transformer, and then we have two feeders. All of these are present in the element list of ETAP right here at the right hand side of your screen. So let's model this system. Now you can see that we have modeled our system with two generators and transformer, then we have a transmission line, and then we have another transformer and two loads. Now we need to assign the parameters to these generators. Generator 1, we can see that it is 11 kV in voltage rating and has a power rating of 20 megawatts. When we open the tab of the generator, you can see that first the thing we need to define is the operation mode of the generator. Now, what is the operating mode of a generator? We need to first understand this. We have four operating modes in a generator: voltage control mode, MVR control mode, power factor control mode, and flow mode. Now we first need to understand the types of buses, and we all know that the buses are defined with respect to four parameters: active power, reactive power, voltage magnitude, and voltage angle. Voltage magnitude and voltage angle combine to form the voltage phase. Now, in a voltage control mode generator, the active power as well as the voltage magnitude is fixed, whereas the reactive power and the voltage angle theta varies with respect to the load. Of course, there is a limit of maximum and minimum reactive power that the generator can supply, but the exact amount of reactive power depends upon the scenario and is not fixed. In an MVR control mode, the active power as well as the reactive power of a generator is fixed, whereas the voltage phasor, that means the voltage angle as well as the voltage magnitude, these are decided by the loads or by the system scenario. These are not fixed. Whereas in the power factor control mode, the active power of the generator is fixed and the reactive power varies in such a way that the overall power factor of the is constant. Now in swing generator, the voltage magnitude as well as the voltage angle is fixed, whereas the active and reactive power can change. Let me repeat, in voltage control, the active power is fixed, whereas the reactive power varies within a limit. The voltage is also fixed and the phase angle is not fixed. In MVR control mode, the active power as well as the reactive power, both are fixed. The voltage phasor is unknown. In power factor control mode, the active power is fixed and reactive power varies in such a way so that the power factor remains constant. Whereas in swing mode, the voltage phasor is fixed, the active and reactive powers can change, and that is why we can say that the swing generator can ideally supply infinite amount of active or reactive power, and this is the reason we need to have at least one swing generator in the system, because the remaining types of generators, they have constant active powers, you can see. So the swing generator will supply whatever power is required in the system, and if the power supplied from the remaining generators is surplus, then ideally the swing generator can also absorb it. We usually refer it as an infinite bus which can supply or absorb infinite amount of power. The swing generator has the AVR as well as the governor installed in the generator, so that any change in the frequency leads to a change in the output active power, and any change in the voltage level leads to a change in the output reactive power of the generator. Coming back towards the generator modeling, the first generator we consider it as voltage control mode generator. You can also see the details of these operation modes in the help menu of ETAP. Here it is clearly written that in MVR control mode, fixed megawatt and megawatt generation in the rating page of synchronous generator. That means the reactive as well as active powers are fixed. In power factor control mode, the generator works in droop mode base loaded, therefore output MVA is fixed. The exciter AVR adjusts to the power factor setting. The generator's megawatt and power factor must be entered. That means that the power factor of the generator will remain fixed and reactive power will be adjusted accordingly. Whereas in voltage control mode, the real power is fixed and the reactive power varies between a maximum and minimum limits. And it should also be noted that if the maximum limit of this generator or minimum limit, that is any limit, is exceeded, then that means the AVR has reached its limit, and now the generator will start functioning as an MVR controlled mode generator with fixed active and reactive powers. So the first generator is voltage control mode, and we can see that its voltage is 11 kV with a power rating of 20 megawatts. Now move towards the rating tab. The power rating is 20 megawatts with a voltage rating of 11 kV, and we also need to specify how much megawatts is the design of this generator and what is the maximum and minimum limit of reactive power that this generator can supply as per its design, normal, shutdown and emergency. So we specify that under normal condition this generator can supply 20 megawatts, and under its design is 20 megawatts, and under normal condition it can also supply 20 megawatts, right? So coming on towards the capability curve, we also need to understand what is the capability curve of a generator. So we all know that the power of a generator is given by S is equal to square root of P square plus Q square, or S square is equal to P square plus Q square, which takes the shape of a circle with the center at origin. The x-axis represents the active power, whereas the y-axis represents the reactive power. We all know that the active power is supported by the turbine, the prime mover, and if the maximum turbine limit is less than that of the generator, then the generator output active power is constrained by it. For example, the generator was capable of supplying, let's say, 50 megawatts of active power, but the turbine was capable of handling only 40 megawatts. That means, irrespective of the generator capacity, the whole system can supply a maximum of 40 megawatt power. Similarly, the reactive power is also limited by the heating limit of the armature, or you can say that the insulation limit. So this is a feasible region which tells us about the shaded region is a feasible region which tells us about the different active and reactive powers that we can get from this generator. The point 1 shows the maximum active power that this generator, the maximum reactive power that this generator can deliver. Point 2 is of course the optimum point of this generator with maximum active and reactive powers, and point 3 is the maximum active power that this generator can deliver. Point 4 shows the amount of power that can absorb, and so is point 5. So moving on towards the capability curve, we assume that our generator is not limited by the prime mover limit. Reactive power is not constrained by prime mover limit, and reactive power is also not constrained. So we just assign it as calculate QA. Otherwise, we need to specify these user defined parameters. And what are these parameters? We can see with the help section that these are QA, QB, QC and QD parameters on the graph, defining maximum active and reactive powers at different points. Impedance model, we need to define the transient and steady state impedances of generator and its reactance and X by R ratios. Luckily, we are using per unit values, and we know that the advantage of using per unit values is that the per unit values fluctuate in a very small range, so we can use typical data, but we need to define that type of generator, whether it is steam turbine, hydro with damping, diesel or combined cycle, and also the rotor type, whether it is salient pole rotor or round rotor. Next comes the grounding tab. We need to specify whether the windings of our generator are connected in delta or star, and if they are connected in star, whether they are not grounded or grounded with solid grounding, resistor or reactor. At the moment, we are considering that our generator is solidly grounded. Inertia is a tab is used for stability studies in the generator. We need to specify the RPM, and WR square is the kinetic energy, and H is the inertia. Since we are not covering the stability studies at the moment, so there is no need to define inertia. Next is exciter. Now there are different exciter types that are available, and same is the case for governor. And if I want to define a governor of my choice, then we just go into UDM editor, and it will open a control systems tab from where we can edit the governor and exciter settings. It will open the transfer functions. Let's select gast.udm. And you can see that it has opened a control system diagram, or as defining different parameters. Now we can add different functions, like we want to add an integrator, we want to add a derivative, so we can program our governor as well as exciter accordingly. At the moment, I am not changing any of these values, so we just go on to the built-in type of exciter, which is fixed, and the governor, which is, let's select it as G as none. So that makes our generator modeling, completes the tab of our generator modeling. In the top tabs, we have PSS, harmonics, and reliability analysis, fuel cost. These are not the mandatory data for power system and short circuit analysis. These are used for different special tabs. So at the moment, we are not considering these values. In the similar fashion, we need to assign the values of generator G2, whose rating is 13 kilovolts, 20 megawatts swing generator, and we all need to assign all the values. Now coming on towards the transformer rating, we go on to the rating tab. The primary voltage has already been assigned because the generator is connected to the primary side of the transformer, and let's assign the secondary voltage as 132 and it's rated MVA. as 30 MVA. So it calculates the full load current itself. Moving on towards the impedance part tab, we need to specify typical values of impedances. Percentage impedance, X by R ratio, that is the ratio of reactance to resistance, of positive and zero sequences. And then we have tabs. At the moment we are not considering any tabs, but we can have the tab changing transformer. Then we have grounding. The primary side of the transformer is connected in delta, whereas the secondary side is connected in Y with a solid grounding. And same will be the scenario for the second transformer. We also need to identify the type of transformer, that is whether it is a liquid filled transformer or dry type transformer. And if it is a liquid filled transformer, then what type of liquid is it? We can select mineral oil and then its class and the temperature rise. Also we can identify specify the derated MVA of of this generator transformer, that is it was designed at 30 MVA rating. It is possible that now at the moment this transformer is operating at a power rating below 30 MVA. Select in typical impedance values and grounding it as delta Y with a solid grounding. Coming towards transmission line, the first thing that we need to specify is the length of this transmission line, either in feet, mile, meter or kilometer. Let's specify it as 30 kilometers. The next thing that we need to define, now there are two options. Either we know the conductor of this transmission line and its per unit values, that is per unit impedance, so we can enter the user defined data. But if we do not have this value, then we need to calculate the values using ETAP parameter settings. Then we go on to the conductor library and we select metric system at the moment. So this is giving you the conductor types, whether you need to select ACSR aluminum conductor, galvanized ACSR or so on. So at the moment we are selecting ACSR conductor. We can also select other types, that is triple AC or double AC conductor. So it's better to have ACSR conductor, and we are selecting gymnastic conductor at the moment. These are the available sizes. So, and next we want to select the ground wire library, and I have selected 3 number 8 ground wire. Here the metric system is not available. Now we move on to the configuration tab. There are different configurations that are available. Horizontal configuration is this one, as you can see, and then we have the vertical configuration. The third one is triangular configuration, and the practically used configuration is parallel vertical, which is a double circuit line, or parallel horizontal. But the practical parallel vertical is normally used commonly, and then we can have the general configuration as well. So selecting at the moment, let's select vertical configuration with the conductor spacing of 10 feet and the height of the tower as 60 feet. Number of ground wires is 1, and the distance between the topmost conductor and ground wires is 20. Grouping, earth and impedance. Now if we have correctly entered the configuration and parameter settings, when we go on to impedance, the impedance of this line will be automatically calculated. Closing it, Now we have already discussed how to select the rating of transformers 132 kV by 11 kV with a power rating of 40 MVA and liquid filled oil type transformer, and selecting typical impedance ratings, and grounding is delta Y with a solid grounding, or we can also select YY with solid grounding. Coming towards the load, we need to select loads of at 11 kV voltage, 10 MVA power rating and a power factor of 0.8. So we go on to nameplate. First of all, we need to specify the connection type, whether this is three-phase load or single phase load. We have selected three-phase loads, and then we go on to the nameplate rating and select 11 kV 10 MVA. That makes 10 MVA. Power factor is 0.8. That means 80%, and 11 kV. You can also assign different types of load. This helps in scenario analysis, like what is the load in winter, what is the load in summer, what is the load in emergency conditions, that is very necessary loads that you need to run. And the one more thing that you need to specify is the load type. Now we also need to discuss what are different load types. There are three types of loads basically: constant kVA, constant impedance, and constant current. There are basically three types of load: constant impedance, constant power, and constant current load. In constant impedance load, the impedance of the load remains constant. That means impedance, which is the ratio of voltage and current, is constant. If the value of voltage decreases, then the current will correspondingly decrease so that the value of impedance is constant. Constant power loads are those loads in which the value of power remains constant. Example of these type of loads are the motors. That means if the voltage is increasing, then the current will decrease, and if the voltage is decreasing, the current will accordingly increase so that the value of power is constant. Constant current loads are those loads in which the value of current is constant, or in other words, you can say that in constant impedance type loads, the relation between voltage and current is inverse, whereas in constant the relation between voltage and current is directly proportional, whereas in constant power type loads, the the relation between voltage and current is inversely proportional. By default, the ratio of constant kVA to constant impedance type load is 80:20 in ETAP, but we can also change this load. Like when we are modeling residential loads, we can consider around 80% or even 100% constant impedance load, or we can change this accordingly. At the moment, we are considering it as 100% constant impedance load, but that depends upon your system. You need to have a detailed analysis of your system characteristics before modeling. So that ends part 1 of this video, and here in this video we learned about modeling of generators, transformers, transmission lines, and loads, and we will be moving on towards the load flow analysis in part 2.